Section 4.5, page 2. If possible, you might want to draw a picture. It kind of helps you see the big picture of what's going on. Ironically, you're always going to have to write an equation for what you are optimizing, but there's going to be some other information so that we can write that optimization question, a function that we just created, with only one variable. Then we're going to find our critical values, and then we're going to determine if they're max, min, or neither. If possible, the second derivative test usually seems easiest because the second derivative of your critical value, when positive, is concave up, meaning a minimum. Or if the second derivative is negative, which means concave down, then you can see you have a max. Otherwise, go ahead and create intervals, test points looking for a change from increase to decrease, etc., to see if you have a local max or min. And then be careful to answer the question as asked. It's not always the value you found. Example 2. A farmer wants to fence in an area for 54 million square feet in a rectangular field and then divide it in half with a fence parallel to one of the sides of the rectangle. What should the length of the sides of the field be to minimize the cost of fencing? Okay, lots going on here. Now we know that our interior wall is parallel. I happen to draw mine vertically, but if you drew a single horizontal parallel line, it's not necessarily going to change the answer. But here's where you've got to be careful. They want the length of the side, so just X and Y are what we're asked to find, but specifically to minimize the cost of fencing. We don't know how much the fencing costs, but when it comes to the fencing, don't forget we've got the 4 exterior sides and the 1 interior wall side, whatever you want to refer to it as. So even though we don't have the cost, the least amount of fencing you use would minimize your cost. So I drew a picture of a rectangle and stuck an X and a Y on, sides that come together at a corner. Whichever you draw is fine. Write an equation that optimizes the item asked for. We're asked to minimize the cost, and we just discussed it's based on the sides. So I have 3 X sides and 2 parallel Y sides that I'm just trying to use as little fencing as possible. Now there should be another constraint that was given to us in the problem. Oh yeah, the question said the area has to be 54 million square feet, which is hard to visualize, but area's 54. Don't put the zeros on. Let's make our life easier. Since they didn't give us the zeros and they used a word, let's continue that ourselves. The formula for the area of a rectangle is just length times width. And I need to take my original optimization problem, and instead of having X and Y, I need one variable. So I'm going to take that constraint function. In my case, I solved for Y by dividing by X. And now I can plug this value into Y to get a new equation. And so if I multiply the 2 and the 54, I'll get 108. And I'm going to need to find a critical value. That requires taking a derivative. So let's go ahead and write that when it's got X in the denominator, we can just make it X to the negative 1. So now finding a derivative of 3X is easy. And negative 1 as my exponent gives me a derivative of negative 108 X to the negative 2. Critical values are when the first derivative is equal to 0. So I'm going to add the 108 over X squared to the right. Think of 3 over 1 so that I cross multiply to get 108 equal to 3X squared. Divide both sides by 3. Take the square root of both sides. And of course it was plus or minus the square root on the left. But we know we can't get negative 6 as the length. Now 6 seems odd if we're talking millions, but remember we're just using 54. Now I have found a feasible critical value of positive 6, but I need to confirm that it is minimizing the cost. So taking that first derivative, I'm going to use the second derivative test where the derivative of 3 is 0, a negative 2 times negative 108 is going to give me positive 216 over x cubed. Plug my critical number in, and regardless of the value, it's positive. That means it's concave up. That means I have a minimum. 6 is going to minimize the cost of the fencing. Now, keep in mind, I'm asked for the dimensions of the whole shape. So even though I only have x is 6, we can go back to step 3 where we found y equals 54 over x, plug our x value in to get y equals 9. Now, it seems like I'm ready to answer the question, but I need to determine the units. Here's where you want to be careful. We were told the total area is 54 million square feet, but our answers cannot be in millions of feet because 6 million times 9 million is way more than, just 54 million. Well, here's where you had to be careful on this one. In step 4, even though you don't see it written over here, I took the square root of both sides, if you remember. So I changed my units from millions to square root of millions, which is 1,000. So I believe the answer should be in thousands. Let's double check. If I took 6,000 feet times 9,000 feet and put those two sets of 3 zeros after 6 times 9 of 54, I do get my 54 million square feet. So the side with the parallel interior wall for me was my X side, which was 6, but we're answering 6,000 feet. And the non-interior wall was 9,000 feet.